All right, guys. So let's hopefully finish up on Verilog. Hopefully, all of y'all have been working on at least your Verilog assignment. If you have not, please get started because the big project of death. I'm trying to think of a better way to phrase that. The hardest project in this course is coming up, and it is a Verilog project where we're basically going to combine all the components you've been writing into one giant Verilog system. Yes?
When?
Soon.
What's TM?
In the future, but not that far. A week or two. By the way, also, you probably all have midterms coming up, right? Yeah, this is the other reason. This is the other reason to get started now, because this will be assigned right around when midterms are assigned, and I know how all of y'all are just going to procrastinate anyways.
He's looking right at me.
Yeah.
So, will this
end of gate 2 or in gate 3?
When does gate 2 end?
It ends 3
March
weeks
17th.
from last Tuesday. So this week's Tuesday.
I probably will then extend gate 2, so it'll finish or end at the end of gate 2. So yes, because I'll probably assign it next week, either Tuesday or Thursday, and then you'll have 2 weeks. Ooh, yep. Yeah. So definitely get started on this. When does gate 2 currently end?
March 17th.
Yeah, so you'll get one more week. Wait, we have spring break.
Yeah.
Yeah, you get another week. I'm not giving you work I give you work over spring break. I just can't expect you to do it.
At least you're realistic.
Right? Yeah, well, come on. Wait, so it was due, so the gate was due at the week after spring break?
It was due the day we get back.
Oh, that's lame.
I always do.
That's the story of my life.
Actually, I might even
Yeah, that ain't happening. That's not happening. All right, that's gonna be moved.
Lame.
Big lane.
All right, so anyways, so far inside of Verilog, we have not talked too much about the always block. We've talked about how to do structural with gates that you put inside of a circuit and they hook up. But there is another way to do a simulation, and this one is not as synthesizable per se as the regular version, but is very helpful for certain types of structures. So it's an always block, and what this is saying is always at. Hey, let's do the little text. So here we got some registers. Statements in the always block are executed in sequence, aka from beginning to end, and that's not going to say anything good. Oh, the sensitivity list. Oh wow, always blocks are sensitive. So in other words, once it senses a change in any of the variables that you've listed in here, it will go and execute the always block. So you can almost think of it as a chain. Whenever there's a change to this expression, aka W or X or Y or Z, aka any of those change, do this execution and recalculate all these values. So you can think of it based on the change of something. So i.e. a change of one of those wires triggers an event. And we're going to skip a bit. There we go. So always block. Ooh, why did some? That's interesting. Cool.
That's awesome.
Yeah. All statements within the block are executed sequentially, unless you are doing a non-blocking, in which case they're all executed at the same time. When is it executed? During that sensitivity list. Let's jump over. And let's go ahead and do a quick little example. So let's go to class code. Let's go into Verilog behavioral, and let's do our good old our D flip-flop. So module D flip-flop. All right. The big point of doing behavioral, at least in this case, is now you're going to have a clock and a reset. And y'all remember what a clock was, is so we could determine or set steps and when execution was complete, and reset is to help us initialize things. So we'll have a clock, we'll have a reset. And what were the other two things that were inputs? Actually, there was one other input to the D flip-flop besides the clock. It was the... Wait, what does the D flip-flop do? Maybe we forgot that. Ooh. I know, we looked at assembly, and now we have to go back to Verilog. We're just jumping around everywhere. I know we are.
It's a little hard to follow.
Well, that's what happened this semester. This will all change next time. So congratulations for taking it this semester. What was the D flip-flop doing?
It flip-flops.
It flips and it flops. But what was it flipping and flopping on?
Zeros and ones.
It uses the
I don't know why they answer this.
You're right, use a clock. It's storing, it's a memory. So it's memorizing or storing a value. So we need to be able to change that value. So we'll call that D. And then it outputs its value, we'll call that Q. Okay. And we could have a Q naught. You want to have a Q naught?
Sure, why not?
Q naught. All right, so we're going to have input wire clock, reset, and D, and then an output wire Q and Q naught. All right, let's see if that actually compiles, because I don't know if it does. Looks like it did. Great. Oh, wait, this is too hard for y'all to read. No one told me. I did find a way to increase the font, but it only increases the font to one size. So hopefully everyone's happy with
Go
that.
on to edit.
All right, we'll try this one more time.
Oh no, it's not there. Never mind. On my version, it had a font mode at the very bottom of edit, so I guess it's not.
Oh my gosh,
Oh.
yes.
It's pretty good. That works. I wonder why it's different from the version.
You know, I have no clue. All right, so now we want to have our always block. Well, when does our always block execute? Always
Always. All the way.
at clock or reset. But we actually want to execute only on the pause edge of clock. I'm going to get rid of reset. Anyone want to take a guess why we do it this way?
Because that's what the real one does.
So actually, oh, I didn't tell you what pause edge means. Come on, guys. What does pause edge mean?
If
Go
I'm
ahead.
not mistaken, when it first gets to one
Oh, I meant for you to
signal-
ask me the question.
Oh, sorry. What's the pause?
I was trying to help you tee me up so I could help
Okay.
everyone. Okay, you're skipping ahead, which is okay.
Sorry.
I got excited.
I got excited. I know, got too excited.
Okay.
So pause edge means, yeah, pause edge. Thanks. Means when the clock goes from 0 to 1, execute this statement. All right. So only when the clock is rising do we execute the begin. And now let me make sure I typed this all correctly because I may not have.
And always like a conditional thing.
Kind of. It's really a list of things you're looking at. So I'm looking at the clock. You can also look at different things. By the way, you can have multiple always blocks inside of a file. So you can have a separate block of code for each different always. So here we could do if reset equals 1, begin. Hold on. I always forget my if statements. How do if statements work? Anyone? No one? Nah, I thought so. Else, end. Let's see if that's how they work, because I don't remember. Nope.
I don't think you need it in.
No, it doesn't like else. What's that? Oh, it needs to have something. Well, we need to have a wire. Actually, we need to have a register. So these need to be registers because that's what they're actually storing. So on reset Q will be equal to 0, and Q naught, wow, that was weird. Q naught should be 1, right? Notice that the assignment here is less than or equals. You can do a single equals. Please don't do that. Things are going to get really weird. And I'll show you what that does in a bit. Otherwise, Q will go ahead and we'll set it equal to data, and then Q naught will be the naught of data. All right. Let's see if that compiles. Nope.
Why do you have that end there? 2 ends.
I have 2 ends. This one ends the beginning block, and this one, is it phi? I can't remember what it is in. You know what? I wrote this so I wouldn't forget. Oh, I have to put begin and end in each of them? Oh, that's so lame. Wow. Think of it as begin as the open curly bracket and the end as the closed curly bracket. Well, that's kind of annoying. Oh well. Let's see if that compiles. All right, it compiles. So So what's going on here is when the clock goes up, if the reset is on, we set it manually Q to 0 and Q naught to 1. Otherwise, if it's rising and the reset line is not on 1, then we just set Q equal to D and Q naught equal to not D. All right? So we need to write a little test module, right? Yes.
Probably good idea.
All right, and then we need to create our own little DFF, device under test. Oh, we got to give it some things. What was it giving it? This is where I like to actually copy and paste it. Good morning. So it needs a clock, needs a reset, needs a D, a Q, and a Q naught. All right, so what are these things? Well, the clock is going to be a register. So will be reset, and so will be D, because those are coming in. And then I'll wire the Q and the Q naught. All right, let's see if that actually compiles. No. Duplicate declaration of clock in DFS test. Ooh, that's kind of cool. Why are there duplicate oh. Let's try that now. There we go. Because I have to declare them before I use them. Silly me. All right, so there's our device under test. And if you remember, it's initial, begin, end. Well, here's where things get a little interesting. Because what do we want the clock to be doing? You're not sure?
Switching between 0 and 1 within a certain time interval.
Right. We definitely want that. Well, one way we could do this is we could have clock equal to 0. Wow, why do I not get tab completion? Equal to 1. And then we'll hold it for, I don't know, 1,000 ticks just for the fun of it. And then we can bring the clock back up and then back down. And then at that point, we can display Q %D and Q naught %D. And hopefully, since we just reset it, we should hopefully get a 0. Let's find out. Hey, good. We got a 0. All right. This is going to start becoming cumbersome because in our next test, we're going to want to do this. And then we're going to want to play this whole game again where we bring it up, bring it back down, and then display it. Ooh, do you see why this is annoying?
Yeah.
All right, well, let's go see if it works at least. It didn't. Womp, 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 womp. Oh, I know why, because I didn't wait the one extra cycle. No, maybe I don't know why. It failed miserably. It's not working. Who broke it? Oh, I know why. We didn't tell reset to turn off.
Oh, reset's been on the whole time.
Reset's been on the entire
man.
time. Man, who wrote this code?
You did.
We soiled it.
You just typed 1 again.
Yeah.
You didn't think it's a 0.
Everyone's a critic. All right, there we go.
Yay.
We can afford to be.
Yes.
Or so you think. All right, so as you can tell, this clock thing is pretty annoying, so let me help you another way to do it. Initial begin. Hey, look, you can have multiple initial begin statements. Isn't that nice?
What?
What? Say what? Okay. Clock equals 0, end. Let's see if that compiles. Yep, perfectly okay. All right, here we go. So an always statement, by the way, you can do an always statement that doesn't rely on anything and only does something based on ticks. And I'm going to write this and then hopefully it'll make sense. Always 1000 clock equals not clock.
Wait, so you can make it run all that every time?
Yes.
So that instead of having to write
Mm-hmm.
Now, what time, when does it do it though? At what point does it?
So this is always, and I'm
Yeah.
putting the finish so that at the end we call finish, and it'll make some sense in a moment. What's the hold on a second, sensitivity list here? There isn't one. So it's always going to be running this over and over again. Except I put in a gate delay. So what this means is that every 1,000 simulation ticks, it's going to run this statement.
So it always wants to run it, but it's actually only gonna run it.
Every 1,000 because I'm delaying it.
Okay.
So now I can get rid of that statement. Well, I gotta keep my ticks going.
I thought the whole point was to have, oh, I
And we get rid of that and that. Okay.
There's there's 1,000 ticks telling it to do the.
So that's
Oh.
so this is doing it every 1,000. This is a separate block execution block. Remember, there's a simulator. Things are happening in parallel.
Okay.
So the always block that's flipping the clock is completely separate than the initial begin. Those are two separate
Okay.
modes of execution, so to speak, or execution paths.
But
So-
after it waits 1,000, then that.
So we can just change this to 2,000 so we don't have to write everything so many times. There we go. And there we have it. Okay. So, for anything that's going to start using the clock, I highly recommend you do things this way. Got that?
I'm gonna write this down. Because you won't submit it. I don't know what that is.
Take your phone out and go
What's a
flip.
phone? I'm just kidding.
We got at
I
least
just
one
know that
guy.
you say you'll submit it, but then I'll have to ask you because you never push anything.
I say I will submit it, that doesn't mean, but I didn't give you a time.
That's true.
So I didn't lie.
Soon, TM.
And I say, yeah, and it was after class.
Will you submit it today?
I didn't say that. I'm not making any promises.
Today after class?
I mean, I'll
That's why I'm
try.
being specific.
Please.
I will try. Don't let me forget.
I'll remind you at the end of class.
All right, any questions? How are we doing? Great. Now we're gonna take this to the next. Well, let's go back to the slides. Make sure I covered everything. Let's see. The inter-assignment delay. Oh, that's kind of amusing. That delays execution of everything. That's the #2 before. I prefer to put the pound on separate lines so it's obvious that this is a barrier and that number of ticks is going to go transpire before or go by before you go to the next line of code. And then the intra-assignment is the idea is that the carry will wait 2 ticks before being assigned, but it doesn't affect anything outside.
Okay, so
In other words, let me help you out. Just stick with this method. Don't try and put a pound like right here. That's going to get a little confusing.
you said it waits to do it?
Yeah, so this is like a barrier, and it waits 2,000 ticks before it moves on to the next line of code.
Okay, so it does it and then it waits. The other one is it waits to do it?
Is it waits to do the assignment.
Okay.
So the assignment is delayed number of ticks. This is execution is delayed number of ticks.
Okay.
Also, before anyone forgets, or before I forget, once you have this line of code up here, you must call finish down here. If you choose not to call finish, the simulator will run ad infinitum. Because it doesn't know to finish because it still has to finish executing this always block, which by the way does not terminate. So that's why you have to call the finish function so you can tell the simulator, we are really done now, go ahead and stop.
You didn't put finish in the module though, did you?
Could we also look at DFFW again?
How come you didn't need to finish in that one?
Because he's not driving simulation.
Oh, okay, because this is a module that the test is actually running something. Okay,
This is just a
got it.
module, it's like a class.
Gotcha.
It doesn't do anything by itself
Oh, okay.
until the module actually instantiates it and starts using it.
Gotcha. It's the initial block, right? 'Cause that's the thing that makes it initial and begin. That's what.
Really, it's this thing. I can get rid of initial begin and they'll just run ad infinitum.
But I meant like what makes it an actual simulation is the initial thing. It's what turns it into
Having an always block somewhere turns it into a simulation. Anyway.
okay.
So the
Simulation
initial,
are the same.
that initial begin does do it technically, but
Okay.
the always block just turns it into a full simulation.
Okay. So the tests we're doing before weren't full simulations?
They were a full simulation, but they were not a system simulation, they were a module simulation.
Okay.
Now that we have a clock, it's like a system because you're pushing a clock to everything.
Okay. Got it.
All right, any other comments? Screams? Excellent. Welcome. Let's see. Two procedural constructs, initial, always, all right. Okay. I don't know what the point of that slide was. And that's all I have for today. Okay, great.
Really?
No.
See ya.
Aw, I was like, wow.
That's all the slides I have. I forgot to do the rest of the slides, so too bad for you. Okay. Now, one of the assignments is going to be to write data memory. I am going to show you data memory because it is weird and annoying.
Great. You just love torturing me.
What do I have in here? Ooh, look at all the code. Oh, you know, I called it this. I think I was trying to be tricky. Okay, how does that look? Okay. All right, let's take a look at this. Wow, these are in the wrong order, so let's fix this first. There we go, much better. And let's go ahead and jump back to our other slide so we can have a picture of what we're looking at, because I get the suspicion that not everyone knows what's going on. By the way, 07 data path, that's going to be your slide to be looking at a lot, if it ever loads. Here we go. So, this is the processor we're trying to put together, and over here we have data memory. What's going to data memory? Tell me the arrows that are going.
Register file.
ALU. The output of the ALU and
With the register.
the output from the register file. All right, there's two other things that are not shown, and those two things are, we just did them with the D flip-flop.
Clock.
And
Reset.
reset. So those are 4 inputs. Let's jump over here. So clock, reset, NA, NB. Oh, there's another one. It just wasn't an input. Wasn't shown. There's an enable wire and a read-write wire. All right. Wow, so that's 6 inputs. Man, this thing's getting complicated. Enable, read-write, and then data out. The data out is this guy coming out here. By the way, we're doing the 64-bit version, so we're gonna have to change these numbers. So, actually, before I start doing that, how many bits are coming from the ALU? It's a 64-bit processor, so there's 64 bits. It's okay. How many are coming from the register file? Louder.
64.
Very good. Okay, sorry. Yeah. All right. How many bits are coming on the enable wire?
64.
No. Oh, fail.
No, wait.
Oh. Sorry. I'm sorry. I didn't mean to jump on you like that.
No, that's it's coming out of the 6 by 64, so it's
One wire, because it's either enabled or disabled, right? We only need one wire for that. How about if we're switching between read and write? How many wires do we need? 1, because 0 is read, 1 is write, or the other way around, whichever one you want to do. All right, so in A is 63, in B is 63, the enable is 1, read write is 1. Let's go ahead and move this clock thing up here. All right, in case this notation is not familiar, this is making an array or a vector of input wires. So there's 64 wires labeled from 63 down to 0. Hey, which Indianness is that? Actually, you don't know. That was a trick question.
What?
It depends. Well, are we ending, is the 0 the biggest or is the 63 the biggest? Well, I mean, we know that from numbers, but that doesn't mean we're encoding it that way yet. That's why this is one reason it's confusing, just so you see things coming down. That doesn't necessarily tell our endingness. All right, I'm being a little facetious. Sure. Here, how many wires is this? 1. From 0 to 0 is 1 wire. From 0 to 0 is also 1 wire. Great. Okay. If you read the memory, let's see what we're doing. There are going to be 65,536 data values, each of which are 32 bytes, or 32 bits. All right, yes, I know we're doing a 64-bit, right. I know it's a 64-bit machine, but the memory is only going to read 32 bits at a time. Yeah, that's annoying and confusing. Well, I was told to do x86, and now we have to deal with it. So what this is saying is we're going to have 65,536 rows. Each row has 32 bytes, or bits, sorry. And we're going to have an output wire that's also 32 bits. Okay. On the positive edge of clock or the positive edge of reset, if reset is 1, begin read min h on program.bin. Memory. Ooh, anyone want to take a guess?
Default values?
Yeah, for the memory. But we're going to read them from a file. So I can show you what the file looks like. They're just a bunch of hex values. Obviously, the top has some stuff. Hey, look. What number do you think that is?
No.
-2.
Why is it a whole bunch of letters?
Because it's in hex.
Oh, okay, yeah.
Because the H
I remember.
right here stands for hex. There we go. So it's going to read hex. So it's going to read that straight into our memory on reset. Now, this data memory module is not finished. Because what does it need to be able to do? What does the data memory need to be able to do?
Store data.
What's that?
Store data.
Store data. So it needs to be able to write or store data. What is it writing? Let me help. I know it's been a while, but I'll answer that one. It stores the value coming in, or at least the lower 32 bits of the value coming in from the register file at the address provided by the ALU. So the ALU gives you which address, aka where in here to store the 32 bits, and then in B, which is down here, gives you, well, you're only going to do the lower 32 bits of that and store that into that piece of memory at that register. So that's writing. The other one it needs to do is read, and it takes the address from the ALU, read from it, and then spits it out to this mux over here. All right, how we doing? Once you learn how this always blocks work, doing the data memory in behavioral is actually pretty easy. Well, not easy. It's not that complicated. It's only another 10 lines of code max in order to get this right. Yeah, it's not that bad. Okay, but anyways, I'm gonna let y'all do that. Also, by the way, write should only occur if the enable line is 1. So keep that in mind. If enable is 1 and the read-write bit is on 1, meaning write, then you actually write to the data memory. Otherwise, you don't write to it. All right? How are we doing? Great. So, on that note, create a data memory module in Verilog. This will be for your single cycle processor, so let's go move that right over here. So data memory, ooh, that's not a good at all. Let's be consistent with the clock and the reset at the beginning. I'll go ahead and move this up here for y'all. Apparently I did not fully fix this. That's not good. That's still not good. Much better.
Don't worry, the formatting gets screwed up and we pull it into ours anyway.
Oh, so it doesn't even matter what I'm doing here?
Yeah, your
Oh,
formatting
great.
doesn't matter in this legislation. When we get it in, we just get asterisks beside description
Yeah.
and deliverable because the bold doesn't come through, and it's basically all just one line. And we have to go in and put in our own breaks.
I've just been throwing
But it's
them
very
back
much
as
so
swaps.
appreciated.
So, I don't need to bother editing stuff.
At least it actually comes through. Last semester, half of the cards I tried to pull in, they just never showed up, and I had to just type them out all myself.
You just like upload that code that you have. And
I will be.
I'll remind you.
All right, this is component for your single cycle processor. I highly recommend keeping all your code together to facilitate your single cycle processor, because at the end of all this, I'm going to say paste it all together and make your processor, aka what I'm going to tell you next week. So create the Verilog file for your data memory and a test file. I've given you a program.bin. Don't let me forget giving you a program.bin. Make sure you test it and then run the test cases and you should be good to go. This one was 3 points because the difficult part of this is keeping everything in mind, how Verilog pastes everything together. So you will spend some extra time if you didn't get it from the slides, but researching how this is all put together. Okay, so we'll save that card. What's the next one? Oh, the instruction memory. I bet you this one's gonna be just as awful looking. Oh no, it's easier, good. Oh, that's right, the instruction memory is easy. Easier. Whew. Be careful with that. I'm still gonna try and format it just. All right. So you have clock reset, you have the address, 32-bit address. Is the program counter 32-bit or 64-bit? Hey, which one do you want it to be?
The easy one.
32-bit it is.
You're welcome.
The instruction coming out 32-bit. By the way, your data memory and your instruction memory are going to have the same values initially. So looking over here, instruction memory is going to have the same values initially as data memory. So they're both going to read from program.bin, just like I showed. But what's nicer about instruction memory is you, from the PC, the program counter, you just fetch that address and spit it out. And that's all you do every clock cycle. That's it. So if you get the data memory done, the instruction memory should be simple. That's why it's 1 point. Okay, then next comes the 32-bit register file. Oh man, we're doing great. Let's put clock and reset right here. So that makes this part easier. All right. So this one is going to be more difficult, but it should be not too bad once you've done data memory. I highly recommend doing data memory for a register file. So the register file, you have 32 64-bit registers.
Okay, there's 32 64 bits.
There it is. Boom. And I don't know why I hit that. 5 bits tell you which register you're reading from. Oh, I'm sorry, let's go to the picture. What's going into the register file? How many inputs? Actually, let me not ask that. What are the inputs to the register file?
2 different muxes.
From 2 different muxes, okay.
One from the selector enabler.
Okay, so we got an enabled bit, so that's 1 bit. Let's skip the muxes now. Up here, where is this coming from? Your instruction. So the instruction's telling you which registers to read from. And there are 5 bits each. There's 32 registers, so you need 5 bits to select each one. So you got the registers, you have the enable bit, and then we have a mux here. Well, these two muxes, what they deal with is this mux here. Let me use my pointer for the people watching video. This mux here tells you which register you're writing to, and this mux here tells you the value you're writing to that register. So this is another 5 bits because it's writing to that register, and this should be another 64 bits. So let's see if that's correct. Nope, write data should be 63, and then out 1, out 2 should also be 63, even though I haven't told you that yet. But the register file outputs one register, 64 bits, and the other register, which is also 64 bits. So it's always reading from those two registers and then outputting the values of those two registers. And then if the enable line is on, then it's going to write from the data that's on the black arrow to an address specified by the blue one. You got that, Holland?
Yeah.
Perfect. Excellent. Will this be on my desk next Tuesday?
What?
Good. Talk. Again, this is for your single cycle processor. I highly recommend keeping all your processor components together to facilitate the creation of your single cycle processor. Definitely create a Verilog file for your register file and test, etc., etc. You definitely want to put this together. Yeah. All right, how are we doing?
Yes.
These are all very similar. These 3 modules are actually very close to the same thing. Yes.
Is it a 64-bit register file?
Yes. It's
Okay.
a 64-bit register file with 32. Why did I say something else?
Yeah, like.
Thank you. Good call. Good call.
You also say with 60, with 32 registers, that's also.
Yeah, 32 registers. I got 32 registers.
Sorry.
Not a problem. All right. And now for the control ROM. Okay. This one might be a little complicated. The control ROM is this part over here. It's not the decoder. It's the output of the decoder. Remember, the decoder was activating one of 64 lines. The control ROM is going to, based on which one of those lines, output the enable wires. Again, use behavioral. By the way, if I didn't make this clear, the modules I'm going over today, you may use behavioral model. All other modules must use structural, but this one's the behavioral with the always block. Things should be a lot better when you're able to use the always block. So here, you're going to have 64 lines coming in. By the way, the control ROM does not need a clock. It's not based on a clock. It's not holding state. Since it doesn't hold state, it doesn't need a clock. That's very important to keep in mind. Unless your module is holding state, ignore the clock. It's irrelevant. Control ROM does not use state, so it just has 64 lines coming in, and based on which one of those lines is activated is the bits coming out here. Now, for this module, you will need to go and look at the different instructions. So for add, you want to, hey, I wonder where that first one's gone. Huh, that should be a 0. In other words, if the bits 0, 0, 0, 1, 0, 0 come in here, then your output is 0, 1, 0, oh, sorry. Let me use my mouse pointer for the people at home. If your input wires are 0, 0, 1, 0 goes to the decoder, that activates that line. And in your control ROM, you're going to output 0, 1, 1, 1, 0, 0, don't care. You can either make that an X or make it a 1 or a 0. It doesn't matter because it's not enabled. And if you go down these slides, you will also see the same thing for AND. Notice that the ALU changes, that's why I underlined it. And you can go through each one of these opcodes and find out what the output should be. The only two that are not in the slide are halt and no op. In those cases, it's all just straight zeros. All right? All right. And that should be 2 right there. All right. And that should be all the modules necessary before we do the big project.
Is the big project the assembly of the single cycle processor?
Yes.
Neat.
It's all going to come together in one giant explosion of happiness.
You were right the first time.
No, I just,
It'll be an explosion.
of happiness. It's great. Architecture loves you, right, Holland? Any other questions?
I have a lot of emotions right now, but I wouldn't consider any of them to be necessarily happy.
Ecstatic?
Wary.
Wary?
Anxious?
Anxious?
Yes. Yeah, anxious to be.
Can't wait to get started?
Need more time. Can't wait for it to be finished.
Can't wait for it to be finished. All right, so you all love this assignment. Great. Any other questions, comments, screams? Screams? Oh, I knew I'd get more that time.
I would say tolerate.
Tolerate? Okay.
I tolerate.
Well, just wait till next week.
I'd rather die.
What?
Great.